All problems in constructing linear functions really boil down to one of two types. Either we have a single point of data and we know the rate of change, or we have 2 points of data and we want to construct a linear function that connects those 2 points. So we'll take a look at an example of one of each. Let's recall that every linear function can be written in the form f of x equals b plus mx. B is the initial value, the initial data, or the y-intercept if you're thinking sort of graphically, and m is the rate of change, or again, if you're thinking of a graph, then you might call the m the slope. And it's also important for us to remember that the graph of every linear function is a line. So here's an example where we have the slope and the point. So the graphical statement of this question might be something like, what function describes the line satisfying that its slope is equal to 6 and it contains the point 2, 13? An algebraic viewpoint of the same question might be, what linear function satisfies the following, that its constant rate of change is equal to 6, and when we give it the input 2, the output is 13, or in other words, it contains the point of data 2 and 13. Let's think of this graphically first. If I just sketch the graph, I know that it should be a line because it's a linear function. It has a positive 6 slope, so roughly something like this, and the point 2, 13 lies on the line. So already I know what the value of m should be. I'm given the slope is 6, and so there's nothing else to compute. At this point, what I can say about my line is that the function that describes it is f of x equals b plus 6x. I still don't know what the b is, and I'll have to compute that somehow. But I do know that its slope should be 6 based on the information I was given, and so I can simply write that down. I can update my function to reflect that fact. So how might I figure out what the b is, what the y-intercept is? Well, I know that the slope is 6, and so what that means graphically is that each time I increase x by 1, I should increase y by 6. We can use this information to work backwards and find the y-intercept. So if I begin at the point 2, 13, since I know that increasing x by 1 increases y by 6, then decreasing x by 1 decreases y by 6. So if I'm wanting to move backward from x equals 2 to x equals 0, so I move over to the left 1, but that requires me to come down 6. And then I move over to the left 1 and down 6. And since I've moved over to the left twice by 1, now my x-coordinate is 0. And what should my y-coordinate be? I've moved down by 6 twice. And so I've moved down from a y value of 13 down to a y value of 1. So I know the y-intercept is 0, 1, and that tells me that my equation is f of x equals 1 plus 6x. We were able to get the function using this graphical approach primarily because the slope was a nice even number. The intercept turned out to be a nice even number. The algebraic approach you may find more reliable. So we'll take a look at that approach. From an algebraic standpoint, we can begin at the same place. We know that the linear function should be f of x equals b plus 6x because we're given the constant rate of change of 6. I don't know yet what b is, but what I can do is use the fact that when the input is 2, the output should be 13. That's the other piece of information that I have. And so I'll substitute those into the equation. If I substitute x equals 2, that means f of x is going to have to be 13. That represents the input being 2, giving the output of 13. But now I have an equation and just one unknown, and I can solve that. So multiplying the 6 by 2 gives me 12, and subtracting that over to isolate b gives me that b should have been 1, just like we discovered with the graph. And that means that the function should be f of x equals 1 plus 6x. What about an example of a linear function between 2 points? The graphical statement of the question might be, what function describes the line passing through the points, say 2, 5, and 6, negative 1? The algebraic standpoint might be that what would the linear function be that satisfies the following? When the input is 2, the output is 5. That's the same as the line containing the point 2, 5. And when the input is 6, the output is negative 1. That's the same as saying that the line contains the point 6, negative 1. We use sort of a combination here of the graphical and the algebraic standpoint to think about this problem. So just to give us a visual of what we're looking at, here's the line that we're after and the 2 points of data that lie on it. It'll be simplest for us to try and first compute the slope and then use that like before to find what the y-intercept should be. The definition of slope is the net change in y divided by the change in x. This is the same as our definition of average rate of change, but the defining characteristic of linear functions is that the average rate of change for any 2 points is a constant. So what's our net change in y? We end at y equals -1, and we began at y equals 5, so that's a net change of -6 in y. And what's our change in x? We ended at x equals 6 and began at x equals 2, and so that's a change of 4 in x. And so that gives us a slope of -6 over 4, or that reduces to -3/2. So let's update the function. We know that every linear function is f of x equals b plus mx, and we just found out that m should be -3/2. So we can give the partial solution that f of x is equal to b minus 3/2 x. But now we're just in the situation we were before. We have lots of different points to choose from, so I'll pick, for no particular reason, the point 2, 5. That is, when the input is 2, the output should be 5. And we'll substitute those into the equation. So if I choose x equals 2, then I get f of x equals 5. And then I have an equation in just a single unknown. So simplifying the right-hand side, I have 5 equals b minus 3. And moving the 3 over to isolate b, I found that b is equal to 8. And that tells me that the linear function was actually 8 minus 3/2 x.